Okay, so welcome. We will start today's session. So the first speaker this morning is Dhruv Mubayi from UIC, and he will speak about new developments in Hypergraph Ramsey theory.
Thank you very much for the introduction. Thanks for the invitation to the organizers. So the talk is exactly what the title is about, what the title suggests. I have a plan. So everything is finite. Everything is finite. The length of the talk, the number of theorems, and the objects under study. So I'll speak a little bit about classical Ramsey numbers, and the talk is about quantitative bounds for Ramsey problems. And maybe tell you some new things on that. And after that, we'll go to generalizations and extensions. Actually, some of these generalizations are themselves very old, questions going back to the 60s and early 70s. They tend to be more difficult than the classical Ramsey problems. So, but they have a different flavor. So I'll go over these questions of Erd&s and Hajnal, Erdős-Rogers, Erdős-Gyárfás-Shelah, and then, if there's time, I'll mumble a few things about one of the main ideas of the proof. The talk is about basically constructions. So I'll say something about how the constructions are made. Okay, so we'll start very simply to fix the notation. The talk is about K-uniform hypergraphs, families of subsets of size K. And we're interested in Ramsey numbers. So if you give me two K-uniform hypergraphs, H1 and H2, the Ramsey number R of H1, H2 is the minimum. And here I'm fixing a lot of parameters and notation for the rest of the talk. There will be more and more parameters, which I'll try to stay consistent with. So try and get a handle on the notation right here. The Ramsey number is the minimum capital N, such that no matter how you color the K-element subsets of the set 1 through N with red and blue, you get a red copy of H1 or a blue copy of H2. And of particular interest will be the case when H1 and H2 are both complete K-uniform hypergraphs. And when H1 is the complete K-uniform hypergraph on S points, that's S points, all S choose K sets, and H2 is the same with little n, then for simplicity, I will write R sub K of little s, little n. Okay, so we have a big graph. That's capital N, and we're trying to find a red S or a blue little n. And just for something that will come up later, but I'll just mention it right now, that the assertion that this Ramsey number is less than capital N is equivalent to the assertion that if you have no red S clique, you must have a blue N clique. So if you think of just putting the red edges as edges and not putting the blue edges at all, then we're talking about independence numbers, at least n. And later we'll see that one of the generalizations is useful to think about in terms of this formulation. Okay, so let me quickly tell you about the main problems in graphs, and that will lead us to the hypergraph case. Oh, before I do that, yeah, so there are some small examples that are known, and here I'm actually listing all examples that are known exactly when the size of the cliques is the same. The so-called diagonal numbers. R33 is 6, we all learned when we first learned graph theory, and there's a couple more diagonal Ramsey numbers. Oh yeah, I didn't define multicolors, but it's the natural definition. You have more than 2 colors. And for hypergraphs, there's only one result, exact result for diagonal numbers. The smallest possible result. When K is 3 and S and N are both 4, it's 13. So if you two-color the 3 subsets of 1 through 13, you get 4 points such that all the triples are red or all the triples are blue. This needed a computer search. Okay, so it's hopeless to figure out these numbers exactly, so the talk is always going to be about asymptotics. So here are the asymptotics for, I put everything up here. So there's 2 main problems, and this will be the main theme for the first 10-15 minutes of the talk when I speak about hypergraphs. The so-called diagonal case and the off-diagonal case. Diagonal case is when the red and the blue clique have the same size. In that case, I call that size little n. And in the off-diagonal case, the red object is small and the blue object is large. So S is small and blue is large. And in the diagonal case, this is the most famous problem in the field. We have upper bounds and lower bounds that are exponential. And the big open problem here is to improve the exponent 4 or the exponent square root of 2 from below. There have been improvements on other terms over the years since basically the 1930s, 1940s. And this lower bound of Spencer and upper bound of David Conlon represents the current state of the art. So that's the situation for diagonal Ramsey numbers. We've had some more success in one off-diagonal Ramsey number, namely the smallest non-trivial one when S equals to 3, R3n. And here we have upper and lower bounds that differ by a constant factor. The order of magnitude is n squared over log n. Upper bound is due to Aitai, Komlosh, and Semeredi. Constructions due to Kim. And in the last 5-6 years, there's been a lot of activity. And today, we even know the upper and lower bounds apart from a constant factor of 4 or 2. I'm not sure what the constant factor. We're off by a constant factor of 4 or 2 between the upper and lower bounds. But that's actually the only case where we know something as far as the order of magnitude is concerned. It's a major open problem, in my opinion, to solve this question when S is equal to 4. So it's well known by various results that for the off-diagonal Ramsey numbers for fixed S, the upper and lower bounds have these exponents, S minus 1 and S plus 1 over 2. I'm suppressing some logarithmic factors. And it's lucky that when S is 3, they match, and we get n squared. But when S is 4, we have a gap, for example, between n cubed and n to the 2.5. And this is a very, very interesting question about figuring out. I don't even know that there's a clear conjecture on which bound is correct. Okay, so that's the situation for graphs. And in hypergraphs, I'm going to similarly consider 2 kinds of problems, the diagonal and the off-diagonal, and tell you something about them. Okay, for hypergraphs, the numbers get bigger. So I want to define the tower function. Tower sub 1 of x is x, and tower sub I plus 1 is an exponential of the tower sub I. So if you look at tower sub I of x, you have 2 to the 2 to the 2 to the 2, where you have I minus 1 2s. And the hypergraph diagonal Ramsey problem, the main open problem I would guess in the field, is the tower growth rate of the diagonal 3 uniform Ramsey number, R sub 3 n n. And here we have classical results of Erd&s and Rado and Erd&s-Hajnal and Rado from the 50s and 60s, which give a lower bound that's exponential in n squared and an upper bound that's double exponential in n. C is always going to be a constant. And there's a method, which I will may get to at the very end, which shows that if you can solve this problem for 3 uniform hypergraphs, you can solve it for k uniform hypergraphs. So somehow there's a way of taking constructions that we have and then increasing the exponent by 1 every time k increases by 1. So the state of affairs for fixed k, for the diagonal case, is similar to the case of 3. Namely, we have a lower bound that's a tower with height k minus 1 and the upper bound with one more 2. And there's a famous conjecture that the lower bound should be improved to double exponential. In other words, there should be a construction. So there should be a construction of red-blue coloring of the 3-element subsets of 1 through capital N, such that the largest red clique and the largest blue clique are both log capital N. Writing this in inverse form. Okay, so this is and people believe that the constructions should exist, that the upper bound is essentially correct, but we haven't been able to get there. I have something small to say about this, and that's, oh, I should say before going forward that I'll be speaking about a lot of results, and all of them are joint with my ex-colleague Andrew Suk. And here's a little theorem that we proved, and that is we reduced the diagonal Ramsey problem to the following very, very, very simple to state off-diagonal Ramsey problems. Off-diagonal Ramsey problems, sometimes you feel they're easier to solve. So we're quite excited when we made this formulation, but of course it's equivalent. So what is the definition I need? The only difference here is the vertex set is ordered. So you're thinking about the set of numbers 1 through n, ordered. And I'm speaking about 4 uniform hypergraphs, sets of size 4. And I'm interested in P5, which is a 4 uniform hypergraph which looks like this. It has an edge, and it has another edge, where the vertices go in order from left in the way I've drawn. And there's something called the ordered Ramsey number. Let me define it. The ordered Ramsey number, OR sub 4 of P5n, is the minimum capital N, where the n is vertices placed in a line, such that no matter how you red-blue color the 4-element subsets of the ordered n-element set, you either get 2 red edges that look like this, or you get a blue n clique. That's it. That's what this ordered Ramsey number is. And it's an equivalent statement. If you could prove that this is double exponential in n, that's equivalent to the main problem about diagonal Ramsey numbers. So we changed the 3 uniform problem to a 4 uniform problem, a diagonal to an off diagonal with an ordering. But the configuration is extremely, extremely simple. So if you don't have 2 red edges like this, you must have a clique of size log n. Okay, so actually this is part of a more general theorem. Here's a slightly more general version of this thing I stated before. You can define an ordered tight path P sub S for K uniform hypergraphs as S vertices V1 through V sub S ordered, and all the consecutive intervals as edges. There's going to be S minus K plus 1 of them, 1 through K, 2 through K plus 1, 3 through K plus 2, and so on. And we define the ordered Ramsey number in the way I've written. And the theorem we proved is actually this upper and lower bounds for the ordered Ramsey number in terms of the diagonal Ramsey numbers for hypergraphs whose uniformity is 1 smaller. This is also a special case of the general result. But if you see this theorem, you immediately see that if you have a bound for the ordered number, you have a bound for the diagonal, and vice versa. So we felt very excited because this problem seemed easy, but of course it's equivalent, so it's not really easy. Right. So yeah, it does. We don't know what the answer is, but it's equivalent. It's an equivalent formulation. Okay. So that's all I have to say about the proof is actually rather short. It's a 1-page kind of combinatorial argument. I mean, once you see the statement of the theorem, I think everybody can come up with a proof if you think about what you have to do. If you want to prove this lower bound, you start with a construction for the parameter you're given with S minus 3 colors, and you produce a red-blue coloring for 4 uniform, If you think about how you might do this, there's only one way to do it, and then that works. And similarly for the other direction. So the challenge was coming up with the statement rather than the proof. Okay, so that's all I have to say about diagonal numbers. Now let me talk about off diagonals, where I have a lot more to say. So we're interested in the classical off-diagonal hypergraph Ramsey problem, the analog of R3n, R4n, and so on for graphs. And there's a conjecture here on the tower growth rate, and that is that for any s at least k plus 1 fixed, the off-diagonal Ramsey number grows faster than a tower of height k minus 1. So the hardest problem in this regime is the smallest s, which is going to have the smallest value, and you need to show that that is at least the tower of height k minus 1. So r sub k plus 1 n is greater than the tower of height k minus 1. And this is an easy upper bound. So there's a rather standard argument by Erdős and Rado in the 50s and 60s using the pigeonhole principle, which gives upper bounds for Ramsey numbers in general for hypergraphs, and it would give you this upper bound. Okay, so this upper bound is well known and easy relatively speaking. So the issue is the lower bound. So when k is 2 and we're speaking about graphs, this is saying that you should have something that's polynomial. It's actually the way I've written it linear, but we're going to be worried about the tower height rather than the exponent eventually. For 3 uniform hypergraphs, that's the first non-trivial case, it's asserting that the Ramsey number, the smallest off-diagonal Ramsey number, is exponential in n, right? Tower sub 2 of Cn. And actually, that's not completely trivial, right? Because you want to make a construction where you have no k4, and yet you have independent sets of logarithmic size. You can't just do things randomly like you might want to as your first attempt. So it's actually a rather ingenious construction which tells you a little bit about how the constructions in this field go, at least one part of them, which is that you need to use a mix of deterministic and randomness at the same time, deterministic construction and randomness at the same time. So this is a classic construction of Erd&s and Hajnal. The way you make such a construction is you start with a random tournament. So you take n points and you order the n choose 2 pairs, either I points to j or j points to I, with a coin flip independently. And then you make, so here are your n points, and you have to make a red-blue coloring or just a red triples. And what you do is if 3 points form a cyclic triangle in the random tournament, you make that into a red edge. And if not, it's blue or it's not there. And the nice thing about this is that if you think about it for a few seconds, you see that if you have 4 points, you cannot even have 3 triples on 4 points, let alone all 4 triples on 4 points. Because if you have 2 triples, they look like this, and then you're out of luck because of the arrows. Now, the thing is not complete. So the tournament is random, but the triples are not random because there's dependence amongst them. But from the point of view of analyzing the independence number of this tournament, you can assume that you have enough randomness to do the standard things you would do as if it were random. So in fact, one can show that the independence number is logarithmic. So the feature of this construction that I want you to observe is there has to be a component of randomness. That's to control the independent sets, in this case of logarithmic size, and then a non-random part which is going to control the non-existence of something small. In this case, it was K4. And this is a theme that sort of continues in the field. Okay, so for 3 it is true, but what happens for larger values? Well, Erd&s and Hajnal themselves showed that the conjecture is true if the small clique is a little bit bigger than k plus 1, well, a lot bigger actually, exponential in k, 2 to the k minus 1 minus k plus 3. So they proved that r sub Sn, where s is this value, grows in the correct tower height. But it turns out that the smallest case in this regime is for 4 uniform, and we're interested in showing R5n is double exponential in n. That would be the conjecture. It falls short just a little bit, right? Because when k is 4, the value that we get is 7. So that construction shows our 7n is double exponential, but not the other values. Now, this was improved quite a lot by Conlon, Fox, and Sudakov in 2009, where they showed that the smallest s is 5/2 k minus 3. So it's not an exponential. But of course, when k is 4, this is again 7. And then a couple of years ago, the 3 authors, as well as Andrew and I, gave 2 new proofs which show the conjecture is true for all s at least k plus 3. But of course, when k is 4, this is still 7. So there were some different constructions, actually. So somehow we are, so this means that we know the off-diagonal growth rate of off-diagonal Ramsey numbers as long as the small clique is at least 3 bigger than k. But there are 2 open cases. And actually, based on what I told you before, that there's a way of moving the uniformity up and obtaining constructions, the whole thing boils down to just these 2 problems. So if you can settle these 2, then you can determine the tower growth rate for all k by some method called the stepping up lemma. So the whole thing is now about R5 and R6n, and we got obsessed with these 2 problems, so we worked and worked and worked, and we made some progress. So here's how the history goes. It was implicit in the paper of Erd&s-Hajnal that this is exponential, and then we proved exponential n squared in a paper, and then we proved exponential n to the log n, and then finally exponential n to the log n. And that's where things stand. We would like to get 2 to the n over log n. That would be double exponential. So we're getting close. R6n, there was a similar state. Erd&s-Hajnal proved exponential, and then in that paper where we had 2 to the n squared, we had 2 to the n to the log n. And then finally, about a few months ago, we managed to prove a double exponential lower bound for R6n, but double exponential in a power of n, not 1. So to summarize the whole story, this is where we stand today. R5n is 2 to the n to the log n. We want to show it's 2 to the n to the 0.1, or anything double exponential in a power of n. R6n, we do have the double exponential growth. And just like I mentioned earlier, once you have it for 4 uniform, you have it for all k, and that's not very difficult. Now there's one little thing we have. If you throw in another color, then we can actually prove the correct tower growth rate even for k plus 1. But throwing in another color gives you a lot of power, so that's not a very, it's not a very surprising thing that you could do that. Okay, so that's how we stand for off-diagonal Ramsey numbers. We just need a construction for R5n, and then we're done. Yeah, I'll say just a brief comment about more than 2 colors. I haven't said much, but I'll be using something to do with this later. So another problem in Ramsey theory is when we have the small clique really small and fixed, but the number of colors goes large. And here here we actually know the tower behavior of it's so-called multicolor Ramsey problem. So the k uniform Ramsey number where you have q colors and you're forbidding an s clique in each color. S is fixed, k is fixed, q is very large. Q is going to infinity. And the issue here is within the tower whether you're growing as a linear in q or q log q. This is a very hard question, I think. The smallest special case goes back to the first paper on these bounds by a famous paper of Erdos and Sekeres, and it's this paper about this question about what is the Ramsey number R3333333. There's an upper bound of q factorial, a lower bound exponential in q, and there have been improvements on the constants over the years, but this is a major open question. Okay, so I'll get back to at some point I'll say, well, something reduces to Ramsey numbers for multicolorings, which is hopeless. I'll be referring to this problem here. Okay, so that's the situation with classical Ramsey numbers. Let me now move to extensions and generalization, beginning with this beautiful, beautiful problem of Erd&s and Hajnal. So what they do is they make, in order to understand these Ramsey numbers, they make the problem a little more difficult by adding an extra parameter. So the difference between this parameter and classical Ramsey numbers is that there is a little t. And what that little t is saying is that you want something red or something blue. The blue thing you want is the same as before, a blue clique. But the red object that you're trying to avoid or trying to find, depending on your point of view, is S points that contain T edges in any way possible. So R sub k S T N is the minimum capital N such that every red-blue coloring results in an S set which has at least T red edges or a blue N clique. Now, of course, when T is S choose K, then we want an S set with all S choose K edges, which is just a red S clique. And so indeed, this gives you Ramsey numbers. But the way that they phrase, the way I've written this problem, you see that there's a host of questions. Namely, you can study the behavior of this function as T increases from 1 all the way to S choose K, and ask what is this Ramsey number. So when T is 1, the question is saying, well, you're not allowed to have an S set with one red edge. That means you're not allowed to have any red edge at all. And so this Ramsey number is just little n, right? Because everything has to be blue. So if you have more than little n points, you have a blue n clique. So when T is 1, this thing is little n. When T goes all the way to S choose K, well, this thing is 2 to the 2 to the 2 to the 2 to the, it's the problem we've been talking about. And therefore, the interesting question here is, how does this change as T changes? And indeed, this was the main problem that Erd&s and Hajnal asked, of which off-diagonal Ramsey numbers are a very, very special case in their famous 1972 paper. And it was a remarkable assertion that they could make given how little they knew about these Ramsey numbers at the time. So the assertion is that as T grows from 1 to S choose K, at the very beginning the Ramsey number is polynomial, it's n at the very beginning. And then the claim is that at one particular value, h1, it jumps from being polynomial to exponential. And then it stays exponential, and then at another particular value jumps from being exponential to double exponential. And then it jumps from double to triple, and so on. So there's this discontinuous behavior with these jumps. And at the very end, before your S choose K actually, even if you're less than S choose K, the assertion was that you get to the bound for the off-diagonal problem. Slight 1 or 2 less. So it was remarkable given how little they knew about this parameter in general. And there's one other famous Erd&s problem in this area, which is what is the value of h1, the very first jump, when things go presumably from polynomial to exponential. And there's a conjecture on what this value is. The conjecture is that if you have S points, then the value of T for which you jump from polynomial to exponential is the value which is equal to the number of edges in the following construction. You take your S points and you divide them as equally as possible into K sets, and you put all these K element sets that go across, and then you recurse this construction inside each blob. You get a number, and that number is supposed to be the number where if you require that many K sets on S points red, then you're going to be exponential. The one direction is easy. That's how they come up with this number. It's easy to prove upper bound. The thing you need is a construction. That's what's lacking. So that was one conjecture, which is still open. There's been some work on k equals to 3, but otherwise the problem is open. And the other conjecture that they had was the smallest value of s, was what these jumps are for the smallest possible value of it. The first case, the first open case, which is when s equals to k plus 1. And they conjectured that when s is equal to k plus 1, these jumps keep happening. As you increase t by 1, you get another exponent. So you get h sub I is I plus 2. So if I'm to write that as a Ramsey problem, then the conjecture was that the Ramsey number k plus 1 Tn is 2 to the 2 to the 2 to the 2 with t minus 2 2's. And even though they made this very bold conjecture, they were not able to do much towards the conjecture. All they could prove was the trivial bounds of exponential from below and a tower from above. That's a huge, 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 huge gap. And it was a gap that was waiting to be narrowed. And so we worked on this problem. And we managed to essentially in all the cases determine the tower growth rate of the Erd&s-Hajnal problem for all except for 3 values of t. All except the very end, because at the very end you are talking about R5n, for example, and we don't know what that is. So we proved that for all t between 3 and k minus 2, the Ramsey number of k plus 1 Tn indeed is 2 to the 2 to the 2 to the 2 to the 2 with t minus 2 2's. And moreover, in half the cases when k minus t is even, we were even able to determine the correct power of n at the very end, k minus t plus 1. When k minus t is odd, we're off by a factor of 2 in the power of n. Here we needed to do something non-trivial. The main achievement here was in the constructions again, but we had to do something non-trivial for the upper bound as well to get the right power of n. And again, the constructions involved randomness at the level of graphs, sort of the way I showed you with the tournament, and then some determinism, which is how you get these towers into the picture for hypergraphs. So that was the Erd&s-Hajnal problem. Let me talk a little bit about the Erdős-Rogers problem. So this was a problem that goes back to 1960s, where they had added a small twist to the Ramsey problem. So we need to define a t-independent set. A t-independent set is a set which contains no complete graph on t vertices. So if t is k, a k-independent set, everything is in a k-uniform hypergraph, is a set which has no complete graph on k vertices. In other words, it has no edge. In other words, it's an independent set. So you allow some edges, but you don't allow cliques of size t. And this Erdős-Rogers function from the 1960s was the same as the Ramsey problem, except you're interested not in the independence number, but the t-independence number. So it's the minimum, it's stated in inverse form here. It's the minimum t-independence number over all k-uniform hypergraphs that do not contain an S-clique. It's a very complicated definition. The most complicated thing about this parameter is figuring out what the definition says. But so let me show you a simple example so you feel it better. So the assertion that f2, 2, 3, n less than little n is the assertion that there is a triangle-free graph. So the 3 means a graph without triangles. The 2 on the top means we're speaking about graphs. And the 2 on the bottom means we're speaking about the regular independence number. So there is a triangle-free graph with n vertices and independence number less than n. And indeed, if t is k, then we get Ramsey numbers. So this is a generalization of Ramsey numbers. Now, the most interesting case here is the case when s and t differ by 1. And for the purposes of this slide, you may as well let s equals to 3 and s plus 1 is 4. So what is f3, 4 asking for? It's asking for a K4 free graph, so you have no K4s, and yet you have so many triangles all over the place that every set of size about square root of n has a triangle. This is the content of this theorem of Wolfowitz and Dudek, Retter, and Erd&s about 3 years ago, where they determined the power for the Erd&s-Rogers function for graphs. So what did they do? What does this mean, this F2 SS plus 1 is n to the half? It's a diabolical construction. It's a graph. It has capital N vertices. It has no K4, right? S is 3, so it has no K4. And yet, every set of size square root of n has a triangle. Okay? Every set of size square root of n has a triangle. That's the bound n to the capital N to the half in this problem. You can't hope to do better than that. And in fact, there are some logs that we added to the mix around the same time. Okay, so you're trying to construct graphs that don't contain a clique and yet contain lots of copies of a slightly smaller clique. So many that if you take a large set of points, you can find one. And that's the Erdős-Rogers function. And so we said, well, what happens for hypergraphs? Well, the numbers change, so you need to define the iterated log function, as I have done. And the same question for hypergraphs, Dudek and I showed an upper bound of log n to an exponent and a lower bound that was much smaller. And Conlon, Fox, and Sudakov improved the exponent from below. But the main open problem here, like with many hypergraph Ramsey problems, is whether you have an iterated log or just one log. It's the analog of whether you have an exponential or a tower. And then we managed to actually do this, but we had k minus 13 logs. So again, this is, let me make sure everybody, there's parameters. So what is the meaning of the statement that Suk and I proved? The meaning of the statement is we gave a construction. What was the construction? It had capital N points. It is k uniform. It had no clique of size k plus 2. So it did not contain a clique of size k plus 2. That's the second smallest non-trivial clique that you could contain on k sets. No clique of size k plus 2. And yet, it had so many cliques of size k plus 1, that's k plus 1 choose k edges, k plus 1 edges among k plus 1 points, so many of them that whenever you take a set of size log k minus 13 times, you find one of these things. Okay? So that's the meaning of this theorem. And the lower bound is taking another 11 logs. It must be right, but the method, I mean, it couldn't be k minus 30. The method works only for, we have some induction, we have a base case. The base case only starts at k equals 16. So we can only, or k equals 15. And that's how it works. Okay, so something open there. Okay, the third problem I want to talk about is, again, a problem that goes back to the 70s, problem of Erdos and Shelah, and then it was investigated subsequently by Erdos and Gyárfás in the 80s and 90s. So this is related to multicolor Ramsey numbers, and that's why I put up a slide about multicolor numbers early on. So here what you're interested in is you're interested in coloring the k element sets of a capital N set in such a way that locally you have lots of colors and globally you have few colors. So F sub k capital N P Q is the minimum number of colors you need to color the complete graph, such that if you look at any p points and the p choose k edges among them, they get at least q colors. Of course you can do this, give every edge its own color, but you want to minimize the number of colors globally. Let's make sure we're on the same page. Let's do a simple example, Fn33. Well, what is that? That's the minimum number of colors to color the edges of a graph such that every 3 points receive the edges among every 3 points, the 3 edges among every 3 points receive at least 3 distinct colors. Well, that's another way of saying that no 2 edges of the same color are incident to each other. So in other words, you're interested in a proper edge coloring. the edge chromatic number of Kn. And the edge chromatic number of Kn is n or n minus 1. So that's what we're interested in, and the reason this is a hard question in general is because in the very simple case q equals to 2, it is equivalent to determining classical Ramsey numbers for multicolorings. Because if q is equal to 2, the thing you're trying to forbid is a monochromatic Kp, and you're trying to ask how few colors can you have so that you have no monochromatic Kp. Every Kp has at least 2 colors. So it's essentially a reformulation of the Ramsey numbers in inverse form. And again here, so the basic question when q is 2 is in some sense hopeless, but the questions that are interesting, and they're related to many other things which I won't go into, is that as q increases from 2 all the way to p choose k, how does the number of colors increase? And it turned out there was one, as the main open question here was when does this behavior jump from being n to the little o1 to polynomial in n? And the conjecture was that this happens at q equals to p minus 1. And this was a problem of Erdos and Gyarfas, and so the first small case was when p equals to 4. So this is again producing constructions. There were some partial results, and then in my first paper that I ever wrote, I proved this conjecture, where I showed f of n43 is e to the square root log n. And then it took a while until Conlon, Fox, Lee, and Sudakov did the general case using some ideas that I had with the construction. So that's the situation for graphs, the very first jump. One can ask the very same question for hypergraphs, and in fact, the hypergraph version of this question is related to Shelah's proof of primitive recursive bounds for the Hales-Jewett problem. Indeed, in the proof, there's something called a cube lemma that Shelah uses, and the assertion of whether you can do something with this particular problem is equivalent to whether you can improve that part of his proof. So actually, the specific problem that relates to that is when p is 4 for larger uniformity. So anyway, there's a hypergraph version of the problem I spoke about on the previous slide, and there's a very similar first transition conjecture for 3 uniform hypergraphs and in general for k uniform hypergraphs, but it's too complicated to state. I'll just state the 3 uniform version. And the problem was posed by Conlon, Fox, Lee, and Sudakov that when you're looking at this threshold, it's much smaller than log n. And the first open case, again, just like it was in the graph case, is when p is 5. And a few years ago, I managed to do the first open case. And maybe it'll take another 15 years to get the thing done in general. But it seems that one needs new ideas. And then the case of higher uniformity seems quite complicated. So again, this last theorem that I stated is a construction, right? It's a construction. It's a coloring of the 3-element sets of 1 through n, where the number of colors is the right-hand side. It's a small number of colors, 2 to the square root log n. And yet it has the property that if you look at any 5 points and the 10 triples amongst them, there are at least 3 colors that you see. And the lower bound is very far from this, so we don't have a good understanding of this function. Okay, so let me, maybe 3-4 minutes. In 3 or 4 minutes, let me try to show you something about how these things are proved. Mainly there's constructions. And let me illustrate it by this theorem that Suk and I had for the Erd&s-Hajnal problem, where we determined the correct tower height for the Erd&s-Hajnal problem. So basically the way it works is that you do something called the stepping up lemma, but you have to have some new ideas. So it's an inductive construction where the induction goes from k to k plus 1. So the key lemma is that the lower bound for this parameter with k uniform is an exponential of the lower bound for the same parameter with k minus 1 uniform. So how does that work? So you start with a construction in the smaller regime. You start with a construction for k minus 1. That's capital N. And phi is the red-blue coloring that you have with that construction. The construction has no red object, which is a k-set with t-1 edges or blue clique. And given that construction, you will produce a construction with exponentially many points for k uniform with the upgraded properties we need. So it's obvious how to make the vertices because you have exponentially many points. If the vertices of the smaller construction were the set 1 through capital N, then the vertices of the bigger construction are sequences of length capital N. So there's 2 to the capital N many points. And then you need to decide, so the vertices are now vectors, 0, 1 vectors of length capital N. And now we need to have an ordering. So we order them based on the number that they represent in binary. So if A is this and B is this, then you write A is less than B. And you need one simple idea. This is all in the everything I say was done in the 1960s by Erdős and Hajnal. This is the so-called stepping up lemma. You need to define, given any 2 vectors, the first position where they differ. So delta of AB is the first position from the left where they differ. And in that position, the smaller one would be a 0 and the bigger one would be a 1 because you've ordered these things. Okay, and you need some notion of minimum and maximum, but let me get to the heart of the matter. How do you cover these things? If I give you k vectors, A1, which is a vector A2, A3, AK, you need to tell me red or blue. And so here it is. You have an edge A1, A2, A3, AK. Each of them are vectors. A1 less than A2 less than AK. You look at these differences, these positions where these consecutive vectors differ, the first positions where the consecutive vectors differ, these positions give you vertices in the smaller hypergraph because that's what positions were in your vectors. And then what you do is if these positions are monotone, you get k-1 vertices corresponding to those k-1 positions, and you copy the color that the construction for the k-1 uniform hypergraph gave. This was 1963 technology. Okay? This is the standard stepping up lemma. Whenever I say something like, well, if you know something for 3, you know it for k, it's because of the first bullet point. But all the non-trivial results that I have told you about today involve some version of the second bullet point. That's the upgrade. Namely, that we add some more red edges. If the deltas go in a zigzag way, we allow that to be red as well. So it's too technical to see why that helps, but that's a common theme in all of the constructions that we make, and that's new. And if that doesn't happen, the color is blue. So this is the upgraded stepping up lemma that's used for the k-13 logs and the other off-diagonal Ramsey numbers and all these things. We use some version of this. And that helps us proceed. And with that, I will end. Thank you very much. Right. Well, so you're talking about this Erd&s-Hajnal problem, is it? Yeah. So because you're talking only about s equals to k plus 1, you can control things a little bit. This doesn't work for larger values of s. Somehow you have to. I mean, it's believable that you may be able. I mean, the zigzag business cannot happen too much, and it's hard to answer it without actually doing the proof.